Hi, welcome to Lecture 2B for Physics 151. The topic of this lecture focuses on significant figures, and I'm going to start off by talking a little bit about what we mean by uncertainty in scientific measurements, and then lead into significant figures as a way of a sort of a shorthand for denoting that uncertainty. The related materials are the sample problems on tutorial 2B and the very last two problems on online homework number 2. However, before we get to the new topic, I have a few quick review questions for you from lecture 2A. So please press pause, try and answer these 4 questions, and then we will quickly go over the answers. Okay, so just quickly, what is the base unit for time in the CGS system? Well, you may remember that the S in CGS stands for second. That's exactly right. Same question here for the MKS units for mass. Well, the K in MKS stands for kilogram. True or false? Weight is the same physical quantity as mass, so the two are just synonyms for the same thing. Well, you may remember I had a whole slide about this, which is no, they're different things. Mass in kilograms is the amount of matter or substance that's present, whereas weight is a force. So weight's measured in pounds or newtons. Density is one of the 7 fundamental true or false, density is one of the 7 fundamental units or base units of the SI system. False. Hopefully you can memorize the 7 base units of the SI system, but even if you haven't, you'll probably remember that density is a derived unit. It's equal to mass divided by volume cubed. Okay, so let's start our new topic. First, let's talk more broadly about precision and uncertainty in quantitative measurements. So, as you know, science is based on measurements of nature. Sometimes those are qualitative observations, but usually we're making numerical or quantitative measurements. Of these quantitative measurements that we make, can we ever measure any of the physical values exactly, perfectly, or does every measurement that we make have some intrinsic uncertainty, or in other words, some limitation on our precision of the measurement? We, in the sciences and in statistics, we often use the word error to mean that uncertainty, but I just want to be really clear, we don't mean error in the sense of a mistake. We just mean it as a synonym for uncertainty on a measurement or on a value. Well, the short answer is there are rare cases where you can measure a value exactly or precisely. And those specifically are when you're trying to measure something that's countable or discrete. In other words, it only comes in whole number values and not in some fractional values, like number of people, the number of chairs, or the number of cars. They have to be integers. So, when the number of those that you're trying to measure is very small, like suppose that there's a classroom that only has around 20 or 30 chairs in it, then you can probably make that measurement with exact precision. So in other words, there's no uncertainty on that value. You might need to count twice or 3 times just to make sure that you're consistent and you didn't make a mistake the first time. But otherwise, once you have made the measurement, you know it exactly. However, even for discrete or countable things, once the number involved gets very large, our ability to measure it exactly goes away. So if you're trying to measure the number of people inside the convention center, for example, at any moment in time, you can probably do it, or the people who run the convention center probably have the tools in place to do it probably to the nearest 100 or so people, or maybe a couple hundred people. But they probably can't get it down to the exactness of, or the precision of the nearest tens of people, let alone the nearest one person. The problem just gets worse if you try and measure larger numbers of countable objects. Also, there's a whole other set of quantities which are continuous quantities. Length, time, temperature, pressure, and many, many, many more. And these are most of the quantities that we're going to deal with this semester in physics and and that you deal with in lab and as you make your measurements. And by continuous, we mean that there's no it's not limited just to integer values, but they can take any value on the entire real number line, if you will. So when you're measuring the length of something, you can measure it to the nearest meter, or to the nearest centimeter, or to the nearest micrometer, or you can go all the way down, and you're limited only by the precision of the measuring device that you're trying to use. Okay? So in other words, how closely spaced are the markings on your ruler, or how many digits are on your stopwatch screen, or what's the sampling rate of your electronic device that you're using to make the measurement. Sometimes there can be other sources of uncertainty that come from the calibration of your measuring device or the way you're applying it that could be systematic, or there can be just fluctuations in the way you're using your device or environmental conditions that can cause random uncertainties. Regardless, all of these things pile into the uncertainty on the measurement of the continuous value. So if you have a continuous value, it will always have some uncertainty built in. And if you have a discrete value, it will almost always have uncertainty when the value is large. And the only time you can know things exactly in the sciences are when they're discrete and small. So now that we've established that most values in the sciences are going to have some uncertainty, how do we convey that on paper or to other people? Well, there's sort of two ways to do it. One is to write out the uncertainty explicitly, and that's what this one slide here talks about. Or to imply what the uncertainty is using significant figures, which I'll get to on the next slide, and that's what we'll be using. So here in this discussion of explicit uncertainty, I just want to say that this is used a lot throughout Physics 151 lab, and they go into it in a lot of detail, and I'll leave it to them to explain this in much greater detail. But we generally do not use explicit uncertainties in our lecture and textbook problems. So an explicit uncertainty is written like this. You write a plus or minus, and then you write a range around the measured value that you think that it is most likely that the true value of this, say, diameter, or the fraction of the population that's in favor of a particular thing. What's that range that you think it's most likely that the true value lies within? In other words, your measurement probably got close to the value, but it probably didn't nail the true value right on the nose. So notice that 6.89 plus 6.89 minus gives you this value and that value. It's sort of like a ceiling and a floor, but they're not absolute ceiling and floor. They're sort of soft ceiling and floors, and I'll mention something more about that in just a minute. Notice that some values are measured with really great precision, meaning that people spend a long time trying to measure this with very, very high precision, trying to get this uncertainty here as small as possible. And that's true for most of the physical constants that we use and other things like mass of the proton, electron, and so on. Other things are measured with relatively low precision. Notice how 3.5 is a pretty big fraction of 47. So this is, kind of like a 7% measurement, if you will. So when you take the size of the uncertainty and divide by the measured value, that's known as a fractional uncertainty or percent uncertainty. And that's what this is here. This is 0.04 centimeters divided by 6.89. Now I said that it's likely that the true value lies in this range. What do I mean by that? Well, it kind of depends on the field of science that you're in. If this value shows up in a physics or astronomy scientific publication, then that plus or minus range probably means the size of one standard deviation on either side of the true value, or the measured value, pardon me, in which case that's about 68% of the likelihood or probability. There's still a 32% chance that the actual true value can lie beyond this range that's cited right here. On the other hand, in other sciences and in other applications like quality control, this might be the cited range here, or interval, might represent a 95% or 99% likelihood. So you just have to know the context and the conventions in your particular field. So let's move on now to, instead of writing values explicitly like this, let's move on to implying a range of uncertainty using significant figures. So just briefly, what do we mean by a significant figure or significant digit? We mean that when it's on a measured value, so when you see a value written down that comes directly from a measurement, then we mean when you see a digit written on the page, we mean that it was actually measured. It was part of the reading that you took off of the ruler or off of the stopwatch or thermometer, whatever it might be, or voltmeter. Digits that are a 1, a 1, 2, 3, etc. through a 9 are always, they must have been read off of your device. So they're always significant. What's a little tricky is when you see a 0 written down as part of a value, was it part of the measurement? In that case, it is significant. If it's just a placeholder that is helping to push the decimal point to somewhere that it needs to be, like, for example, if you were writing down, if you were writing down a value for millivolts, you might need to push the decimal point far off to the left somewhere. So you might put in some leading zeros. In that case, those zeros are not measured. They're not actually significant. They're not part of the value that you were reading off of your voltmeter. If the number that you're talking about came out of a calculation, well, then you're not talking about what you read off a device, right? At the end of a calculation, especially a long one, your calculator screen might have a whole bunch of digits that are listed as part of a long decimal. And what we want to do is we want to round off that decimal to an appropriate number of digits that is roughly reflective of the number of digits that were in the real measured values that went into the calculation. So for our textbook problems and sample problems, what that means is if you use a physics formula and you plug in values that are considered measured values, right? Like maybe a certain number of meters or a certain number of seconds, and at the end of all this, you get out a calculation of a certain amount of kinetic energy, for example. And your calculator screen gives you a whole bunch of digits. You want to be able to round that answer off to something that is reflective of the fact that the values you plugged in were only known to 2 or 3 digits. So we'll have some rules coming up about this on the slides in just a minute. So when we write a number where we decide to stop writing, the location where we decide to round off implies the precision as stopping at that location and as being roughly plus or minus 5 in the next unwritten digit. So here's a few examples of this diameter from the previous slide, but I've written it with 2, 3, and 4 significant figures in these 3 examples here. If you see a value written to 2 sig figs like this, what's implied here is that the next unwritten digit can range somewhere like plus or minus 5. So in other words, minus 5 would be 6.85, and plus 5 would be 6.95, although I've rounded it down to a 4. And what we're saying is that if we were to round any of these values, 6.92, 6.88, any value that lies in that range, if we were to round it off to the nearest tenths place, it would look like that. What if, on the other hand, you see a value that's written out to the nearest hundredths? Well, in that case, you're saying that, well, the range of possible values that this could vary by varies in the thousandths place, right? Plus or minus 5 in the thousandths place. So notice that that's 10 times more precise than in the previous example. And then finally, if there's another digit like this, then that is yet another 10 times more precise, or 100 times more precise than the first one. So we would say that a number that's written to 4 sig figs is 10 times more precise, or reflects a precision that's 10 times better than 1 to 3 sig figs, which is in turn 10 times more precise than a value written to 2 sig figs. Well, how can you tell when you look at a value how many of the figures are significant, or digits are significant, and how many are not? Well, there's two sorts of methods. The quick, simple, and sure method is on this slide, and that is convert first to scientific notation, and then look at the mantissa, and all the digits you see in the mantissa are going to be significant. So here's Avogadro's number, written to a variety of different numbers of significant figures. And notice, as long as we've written this in the most compact conventional form, right? In other words, so the decimal place follows the first non-zero digit, then notice all of these digits here in the mantissa, all 1, 2, 3, or 4 digits, they're all significant. Suppose you have a value that is not initially in scientific notation, like 200,000, then you want to convert it to scientific notation to be able to see how many digits are significant. Well, when you see a value written like this, unfortunately, especially in regular sort of non-scientific writing, so if you see it in like a magazine or a news article, then this doesn't tell us whether this value is measured to the nearest, rounded off to the nearest 100,000, or if it was actually measured with precision to the nearest 10,000, or maybe it was measured actually with lots of hard work to the nearest 1,000, or even maybe with even greater precision. But by casting it into scientific notation, that ambiguity goes away, and you can tell at a glance. This is exactly 1, 2, 3, or 4 significant figures, and you know what level of precision the demographer has actually measured the population of the Big Island to. If you don't want to write the number in scientific notation, then there's a complicated set of rules for trying to decide whether a zero is significant or not. Just going through this quickly, non-zero digits are always significant. The zeros, if they're leading in front of a decimal point, then they're just there to help your eye see the decimal point, and I call those cosmetic zeros. They're not serving any mathematical function, and they weren't measured. If they're between the decimal point and your first non-zero value, then they must be placeholders. Their job is to either, you could think of it as pushing the decimal point off to the left, or you could think of it the other way as pushing the non-zero values over to the right. On the other hand, if you have a zero that comes between two significant digits, like this 1 is 1, 3, or that 7 is 5, then all of those sandwich zeros must have been measured also. In other words, if the start of the sandwich and the end of the sandwich were measured and are significant, then all the contents in the middle of the sandwich must be as well. Here's an example where, following a later rule here, we know that this last zero here is significant, and therefore everything sandwiched between the 7 and that 0 must also be as well. Trailing zeros that appear after a decimal point somewhere, the only reason that they are on the page must be because they were measured. They're not serving any placeholder purpose or any cosmetic purpose. So they must be written down because they actually were measured. So here are some examples of those. Finally, here's the ambiguous case that I was talking about before with that example of 200,000. Suppose that you have trailing zeros and an unwritten decimal point. Well, then you can't really tell with absolute certainty whether any of these zeros here were measured or not. All you can tell with certainty is that the 6 and the 8 were measured, And so this value has at least two significant figures. We can assume that it's probably the case that all of the zeros here have been rounded off or unmeasured. So when you see a value like this, like 2500 or 500, well, yeah, or 500, you can assume this is just a 2 sig fig value. This is probably just a 1 sig fig value, although it might have more. So you can just make that assumption when you see me writing values like that on the page or during sample problems. Physics teachers have a special shorthand that they use to try and solve this problem. And that is, if they add a decimal point right here, then that's the way of telling the reader that everything, that all the zeros that are in the value before the decimal point are measured and significant. So, in other words, a value here, like 500 meters per second, it's ambiguous whether it's more than one significant figure, but if you see 400 point, that means all of those are significant. Done. No question. All significant, all significant. So I recommend you pause right here and try problem 1 on tutorial 2B. It asks you to identify the number of significant figures in a whole series of different numbers. Do as many of those as you wish, check your answers, and then resume when you're done. Okay, the last topic now for this lecture is a summary of what are the rules that we follow when we're combining values with different numbers of significant figures and combining them with an arithmetic function like addition and subtraction or multiplication and division. For other math functions, just to let you know, there aren't any firm rules. So if you're taking a value that has, let's say, 3 significant figures, and you're taking a logarithm of it, or a sine or a cosine of it, then there are no rules, but the general advice is to round your final answer to 3 sig figs as well. So that the final answer coming out the math function has the same number of digits as what you gave to the math function. The rules for multiplication and division are the simpler ones. So let's talk about those first. First of all, look at all of the values that you're about to multiply or divide together. Identify the number of sig figs in each value. Then, examining all those numbers of sig figs, find the one that is the fewest. Then, round your final answer from the division or the multiplication to that fewest number of sig figs. So here's a couple quick examples. Suppose we're dividing 8.0 by 2.40. We identify that the numerator 8.0 has 2 sig figs and the denominator 2.40 has 3 sig figs. Our rule says find which of these values here that we're dividing together has the fewest significant figures. And the answer then is 2 sig figs, which means we round our final answer to 2 sig figs. That's it. By the way, this is an example of a repeating decimal on my calculator screen. 8 divided by 2.4 gives me 3.333 forever. It is not appropriate as a final answer to a physics problem to write the final answer as 3 1/3 or 3 with a bar over it to imply that it repeats forever. Instead, you need to round this to a reasonable number of significant figures that reflects the fact that the 8 and the 2.4 themselves are not perfect numbers. These are values that were measured with some finite precision. That's why the final answer can't be allowed to be a perfect exact value or a decimal that goes on forever. One more example for multiplication. Suppose we have a 4 significant figure value multiplied by a 1 significant figure value. 1 is clearly the least precision, the fewest number of significant figures, so therefore we round our final answer to 1 significant figure. The rules for addition and subtraction are a little more complex. First of all, because we're going to add or subtract values, we need to make sure that they all have exactly the same units, same metric prefixes as well as part of those units, and are all converted to the same power of 10. So that way we're adding apples to apples to apples. If you have values that aren't super big or super tiny, then I recommend just avoiding scientific notation for the purposes of this math that's coming up. Okay. Next, look at each value and identify where the decimal place is of the last significant digit for that value. Then comparing all of those decimal places to each other, find the one that's located in the leftmost or highest decimal place. In other words, the one that reflects the least precision or the worst precision. That's where you're going to round your final value. So here's an example down here. Notice we have 96.6 plus 7.2. And this works if you have 3 or more values that you're going to add or subtract together as well. Notice the first term here is it's written with a precision in the tenths place, and the second value is written with the precision also in the tenths place. So these two are tied. They basically are both written with the same precision, which means we're going to round our final answer to the tenths place as well. In other words, if we measure a certain number of milligrams to the nearest tenth of a milligram, and you add to that another quantity of stuff which is measured to the nearest tenth of a milligram, then the sum of all that stuff is known with the precision to the nearest tenth of a milligram. You might notice that our final answer here is 103.8, which has 4 significant figures, whereas the two values that I added together had 3 and 2 significant figures, respectively. So we gained a significant figure. So this can happen when you're adding, especially if you're adding a bunch of different values together, you can end up gaining significant figures just due to the carryover effect of addition. Or if you're subtracting 2 or more values, you can end up with fewer significant figures in your final answer. If any of the values you're using are negative, then that could reverse these two effects. Let's look at 3 more quick examples, and then this will be the end. So here's another addition. The first value is expressed to the nearest tenths place. The second value is expressed to the nearest thousandths place. And now we identify which of these has the worst precision, right? Which one is the higher decimal place, and that's the tenths place. So we're going to round our final answer to the nearest tenths place. There it is. For subtraction, we follow the same rules as for addition. We have a value that's written to the nearest ones place. Remember, this is the physics teacher notation. So that decimal place right there means that the 0 is significant. So a value that's written to the nearest ones place, subtracted with a value that is written to the nearest hundredths place. The ones place is the worst precision. It's the higher decimal place. So we're going to round our final answer to the nearest ones place. I'm sorry, there's a typo here. That should be 14. But this is the correct answer. Finally, we have a value that's written to the nearest hundredths place, differenced with a value that is written to the nearest tenths place. So therefore, tenths place is worst precision. We should round our final answer to the nearest tenths place. And that's exactly what we did here. And here's an example of losing a bunch of digits due to subtraction. Right? Notice how the original values had 6 and 5 significant figures respectively, but my final answer only has 3. Okay, so that concludes this lecture. At this point, please return to tutorial 2B and look at problem 2, which has some examples of additions, subtractions, multiplications, and divisions for propagating significant figures through those examples. And then, if you haven't yet, go back to online homework 2 and just answer those last 2 questions that are on significant figures.